Okay, there's a couple things I want to go over this morning, and so I'm going to give you the rundown of what we're going to do in this class session. I normally do a kind of a full lecture on the physical layer, and I kind of incorporate some information on undersea cabling because I think that is pretty amazing how that works. I found a really good video that is about 6.5 minutes long, and it completely lays out the undersea cabling and all the good stuff, and leaves out all the boring engineering stuff. And so I'm going to show that video instead in a minute. But first, what we'll do before we get to that part is I want to look at packet tracer 2.76, and physically there was a question about how do I reset the activity that will reset the whole thing. Also, how just to reset the switch configuration, okay? So that you can maybe start over on just one device. And then also in this, quite a few of you had an issue with it scoring the, you just didn't get credit for the enable password. So we're gonna check that out. I want to show you a couple things on that. So
so even though there was a check mark there, it didn't give it credit?
No, there were some people that didn't get a check mark. So I'm going to go over why that happened.
Oh, okay.
Some of you had no problem with it. About 6 or 7 of you were not able to get credit. So I'm going to talk about that. And then if you were one of those people who didn't work for, you could resubmit it. Another thing, just I got the video recorded from last time, and I want to show you in Blackboard where I put it, because I think some of my online students missed, either they didn't watch the class video or they missed the fact that I uploaded a video telling exactly how I wanted the packet tracer assignment submitted. So I'm gonna show you where that video is. Okay, so submission. And then if we have time, and I think we will, I'm gonna give you a big overview of the OSI model in my terms, okay, and not Cisco terms. Okay. So let me share my screen here so everybody can see it. I'm in Blackboard. Am I sharing Blackboard? Okay. So this was where I put the shortcuts, just where I just typed them out. Those are there, the control copy, control paste, control V for paste. That's that first link that says shortcuts for packet tracer and screenshot. And then I made another. Sir?
When did you post that?
I posted it Thursday. And
referencing the video.
And then also there's a video. No, there's an actual video I made, shortcuts to complete packet tracer. And that's a YouTube video. And that goes through and shows you how to submit and what I'm looking for. And
is the video gonna give you?
So that one will take you through that whole part that I didn't record on Thursday. So if some of my online students, I think all you guys got it. Some of my online students did not get the submission right. So, and I'll go over this also. What I'm looking for, just to show you. Yeah. Okay, so again, here's packet tracer. You go to check results. I want the assessment items. And it's okay to make that a little smaller and then take this window. Right, that's what I'm looking for here. Okay. And that video will show you how to do the screenshot. And so this is my 2.76 packet tracer. Now, when I'm in this, if I click this reset activity button right here, I'm going to completely reset the activity. If it has a automatically generated set of IP addresses or code, some of them have like 5 different versions. If I click that reset activity, not only is my configuration going to go away, I may get a different version of the activity. It's all basically the same, except sometimes the IP addresses might be a different network or the host name may be different, but everything else would be the same on the activity. So if you click that button, it's just going to completely take you back to start. So just know what that has the capability of doing. It's one of those things. It's like it's not a bug; it's a feature, right? All right. So if there's another way to reset the activity beside that button, and I may just want to go and just reset the switch configuration. So what I'm going to do is I'm going to get into this switch and go ahead and give it another host name. I'm going to call it S2. And notice that the switch configuration immediately changed. You guys all saw that in the homework. And so what I'm modifying right here is the running configuration, which is in memory. And if that switch powers off right now, because I haven't written the configuration to memory, I get nothing, right? It's just gonna go, and so I'll show you this. So I changed the host name. I'm gonna exit. I'm still at S2. So what I'm going to do is I'm going to go over here and I'm going to click on S2. Now, in this particular situation, I don't have the, I would normally have a physical mode that I could see.
I've got a question.
Sure,
Did you rename S1 to S2?
I did.
Okay.
Yeah, I did. did that kind of upset the balance of the world at this point? Yeah.
Now, how did you back out of this particular view to your physical view there?
How'd I do it?
Oh, wait, never mind.
It's
see.
not visible. I use
It
the
is visible.
logical physical tab.
Got it.
But this particular switch this particular model of switch doesn't actually have a power switch. So let me see. Sometimes on the packet tracer, you can click and there's a physical set. I mean, you can actually physically click the power switch off. Okay, that's what I'm getting at.
Got it.
Right? But that's not the best way. Like if I'm going through and doing a configuration and I've already written that configuration to RAM, I've already done that copy running config startup config. So if I press the power switch, right here, I haven't done that right. So if it restarts, it's going to go back to normal. Okay?
And that's if you haven't copied it to NV right.
Yeah.
Okay.
So if I notice the command on that, reload, right? It says halt and perform a cold restart. Okay, so if I had not written anything and I did a reload, it gives me plenty of opportunities to say no.
Now, what about if you can't even get into the CLI because you're locked out thanks to the password? Because that's what happened.
Oh, yeah, okay, so that is a situation where you start over.
Yeah, that's what I had to do.
Yeah. So because you don't have that now, now in real life, right? Okay, so there is a way for me to go in and get into the bootloader of the switch and actually modify a register.
Mhm.
Modify that register with a specific memory value. It will reset the password. So if I have a real switch, I'm not completely out of luck. I can go reset the password. But what that requires is it requires physical access to the room, which assumes that I have some level of access to go in and reset the password.
Right, so in that particular case, you'd be a physical connection, and you would just get on one of these
Yeah, I have to have a console for it. Right.
consoles.
Mhm.
Right,
Right.
so you're gonna
And
just have to do that.
no, there's a document that we could do it if you wanted to, but basically it would be something we could do after class, but it just goes through and you get into the bootloader by pressing a key sequence, and then there's a single command that you do.
Okay.
Okay, so let's see, I don't know. Now that actually, I guess it automatically wrote because I'm still sitting at S2 as the name of the switch, so let's see. So supposing you could get in, right? There's also the delete command or erase. So I could go in and type in delete flash when I press tab there to fill that out. But let's see. Delete flash, enter. That should do it right there. Okay. Error deleting flash, no such file or directory.
I think
Huh.
it's just listed as config. If I remember correctly, I saw that, hang on a second.
Can I ask a question?
Sure.
So you're deleting flashes, that is, you showing us because how you would get, if you lost or forgot the password?
If you forgot the password, you're never gonna be able to get into this part.
All right.
But if I wanted to remove the configuration and start over,
Uh,
I could do it this way.
okay,
by deleting
all right,
it.
okay.
I could also do erase. So, erase
You gotta go downstairs. You gotta- Come on.
and start a config, that will erase that file. So erasing the NVRAM file system will remove all configuration files. So, that basically was it. It's a way to blank it out. And I did it on just that device, not the whole erase, startup config. Okay. So, couple things here. The people that did not get the password, and I think the reason why, okay, so use Cisco for the console password, use class for the privileged exec mode password. So there's two enable commands here, okay? There's two. Enable password and enable secret. So if I do enable password, which is probably what you did, it should have been what you did if it didn't work for you. Let's see, class. No, I gotta be in configuration mode. So what happens is the behavior in this case is the same if I do enable secret versus enable password, but I cannot encrypt the enable password.
Now, hold up, you're using a command that I haven't seen yet. What is do show run?
So show run is the way I can look at this running configuration
Right.
from the enable menu. It doesn't allow me to do show run from the configure submenu. Do show run will bypass that control and allow me to do what I'm doing is I'm doing show run, right? I'm actually going through and doing that command in a different mode.
Oh,
So
so is that applicable to all modes? Or is it just at
yeah.
nodes that are at a lower level than it?
Yeah,
Okay,
yeah, it should work between all modes. So what happened here is the set service password encryption, it actually encrypted it. So that part worked, but again, this is let me show you what this looks like. It's a little bit different. Okay. So this is easily breakable encryption. Okay, it's nothing secure. Don't think that this is secure. It's not. Okay. I'm gonna make an enable secret. And it's gonna be Cisco 1. Now, here's what happens is when I get enable secret, I get a completely different encryption method on my password. And it is a secure encryption method. Okay. This is just enciphered enough so that someone who's looking over my shoulder or watching me, can't figure out what I typed in by looking at the numbers. When I do the secret, it's actually encrypted. So let me do no service password encryption and turn that off. It's still encrypted it. Let's see. No. This password encryption. Yeah. It's still coming up encrypted. But here's what I wanted to show you. The difference in the command is that the people who typed in, I got a password, so I'm going to use the enable password command. It did not grade that. It didn't grade it. So it's looking for enable secret. So if you read this and said, oh, okay, I need my enable password to be, because you keyed off this word right here. And so you use the command enable password. It's going to grade incorrectly. The right command is enable secret. And that's not a bug. But the difference between the two is that the secret is actually a secure method of encryption. This is a type 5 encryption, which should use MD5, which is a one-way hash. And this is a type 7, which is easily breakable. Just to show you how easily breakable it is. There's a gazillion tools out there. I think this is like one of the first projects in computer security that some people do. Okay. So
Yeah.
not secure. Another thing about packet tracer that I'll show you, if I go show run, and I go ahead and space through all of it, and I go up here to the current configuration, and I just drag, I can copy this over to a text document. This is what you call backup. Okay, so this is a backup control method right here. This is actually what people use in real life in the field. Notepad. This is your backup. Because all the commands, but I can paste this into the configuration of a switch. All right, so if I have a console open and I'm looking at a terminal, we'll do it. So if your computer crashes in the middle of your configuration or your switch goes haywire, you still have the config. And so I don't have to do this version command here, but I can start with the first command. I can copy this. And now what I'll do is I'll jump into switch 2 over here. I'll get into configuration mode. And it says enter configuration commands 1 per line. So I'm just going to go ahead and paste. I noticed I got a couple of errors here, right? It's telling me that you can't turn login on until the password gets set, right? So you guys may have seen that. But what I have is I have a configuration that I pasted in now. Because the switch that was before, it didn't have the no service password encryption. It has my password in here now. They're the same. My switch name changed to S2. So if you're in the process of configuring your switch,
That would save a lot of time.
yeah. And another thing that happens, and everybody thinks I'm joking, is on the final exam, there's a simulated glitch. And I used to think that this was a real problem with the activity, is that the thing will crash right in the middle of your test. And it does it every time. And I realized that while it may be a bug, it's a perfect simulation of real life. Because that's what happens. You get into where you're configuring and you're doing stuff and you're not paying attention, you're not saving anything. And all of a sudden, something happens and the switch reboots and you lose your stuff. So I'm going to say this now, and I always say it. Use your notepad, copy your configuration, and I could, if I wanted to go in and configure things, I could use this skeleton to do my configuration. Right? If I wanted to turn chunking on or do whatever I wanted to do on interface 14, right? I could do some configuration right here. Okay. Right, whatever I wanted to do, I could go ahead and type it in. Let's change the host name on this switch, right? I'm still on the notepad. The next thing I have to do is I have to go and just paste it into my switch, and I got my configuration. Right, so what did we have? We had a password on this console. Right, I can I could be in the switch. I could also do the configuration right here in the notepad. So, if your hands-on final bugs out on you and you lose all your stuff and you got 5 minutes till the submission deadline, and you come to me and say, Mr. Darden, my packet tracer crashed right when I was trying to press save. I'm gonna say, oh, sorry. You should have used the notepad to copy your stuff, okay? So, but here's what happens. Now that I got that enable secret, oh, I don't think let me, I think I put, okay, so in that case, I put the wrong enable secret. Okay, so we're going to config mode, enable secret class. So what I'm going to do to get around that error message is I'm going to say no enable password. I'll turn that off. Enable secret class. Now I have enable secret. And I got credit for that. So let's see. The folks that did enable password could not get a check mark right there for no matter what they tried. So I think I had some folks who try to do this activity like 3 or 4 times because it was not checking that box. So, okay. Any questions on that at all? Any question on anything that I just did? All right. So undersea cabling. This is that look at the physical layer. What I really want to do is kind of show you more about all the processes that go into making this internet function the way we want it to. We have in layer 1, in this physical layer, we have we have the network cards and we have the switches. We have wire, we have fiber. There's a lot of technology that goes into making this physical layer what it is. One of the most notable examples of that is SpaceX. Okay, so we got a company, SpaceX, that is one of their jobs is they're reducing the cost of putting satellites into space. And the first thing that they decided to do was, let's see if we can create a reusable booster rocket so that we could land that rocket on a platform or on a ship and reuse it. And every time we can reuse the rocket, it cuts the cost of production by a large amount. I don't know what that is, but it's a huge amount. So it's reducing the cost of getting things into space. And so we have a large amount of satellites up in space. That's part of the physical network layer. We can communicate with those satellites. And one of the things that SpaceX is doing is they're creating things, if you've ever heard of Starlink, okay? Starlink, some people, like a lot of astronomers can't stand them because they're polluting the night sky, okay, with all these constellations of satellites. But other people really like the ability to get high-speed internet anywhere in the world. And so this is a low Earth orbit satellite system. This is the physical layer of networking, right? We have this orbiting satellite up in space. Okay. So another component. Now, I want to ask you this question. How many jobs do you think are somehow perpetuated by, financed by, or otherwise, how many families are supported by this the engineering marvel right here with Starlink?
What do you mean? Like how many people went into the design, production and servicing?
Yeah,
Hardware engineers, software engineers, obviously the rocket scientists, so you got hardware and software engineers there.
right.
You got obviously the network administrators for the Starlink system itself. And you got more software engineers on top of that.
Yeah. Yeah, you got it, right? So we got talent, we got
Ship pilots, all that.
all that, right? All that in this process of I'm putting some satellites into low Earth orbit. This is the physical layer of networking. This is the last mile, so to speak, between no internet and commerce. Okay? So these guys are doing it.
There's a guy that I do some gaming with who lives in Nova Scotia that uses that.
And is he able to do everything pretty good? Yeah, okay. So one of the things that we hear in the satellite space was Dish had an internet service and HughesNet had an internet service.
Yeah, they still push use quite a bit for the rural.
And the issue is that, and this is the difference between low Earth orbit and middle Earth orbit, is that in order for that satellite to be geosynchronous to where it covered a specific portion of the United States, it had to be high in orbit. The Starlink satellites were able to be low in orbit. And so what ends up happening is that the difference between the two is latency. There's less latency to get to the Starlink satellite, which means that I can do all the things that they're talking about, streaming, video calls, and online gaming. With HughesNet, I could never do that.
Yeah, the issue with Hughes was the fact that you had a delay in between input and actual.
Exactly. I would click a link and it would take maybe a second or more for that. In the internet world, a second is a long time. Okay. So, and this is pretty big right here, this self-install, right? So the fact that my customer can actually install the equipment is huge. In a normal customer premises equipment wireless setup, I would have an installer that would come out. He would screw something to the root, run cable, and it would cost about $300.
Play with a signal strength meter.
Yeah, or you have to aim it the right way. You got to use GPS to figure out where it's pointing. This puts some of that on the customer, but it allows for allows them to get more customers faster. So
I know that you already know this, but what do you think about the guy that used like $5 worth of stuff he bought off of Amazon to hack those little receivers? for the transceiver.
I thought that was pretty creative. I think that
Yeah.
he's gonna get himself in trouble.
Yeah.
Okay. So that's SpaceX, Starlink, okay. There's another part of this, and this is the undersea cabling. So I'm gonna show you a little video. It's about 6 minutes. And we'll talk about it.
99% of all internet traffic, from this video to your Pokemon Go account to your family WhatsApp group, runs on a hidden network of undersea cables. Why should you care? Because modern life is increasingly dependent on those slinky subaquatic wires. And they get attacked by sharks from time to time. How do they work? What's the future? Join us today as we plunge the depths and ask how the internet travels across oceans. According to the authoritative Submarine Cable Map website, there are currently 493 active or actively under construction subsea internet cables crisscrossing the globe. These range from the relatively modest 300-kilometer Azerbaijan to Turkmenistan wire running under the Black Sea, to the absolutely gargantuan 6,600-kilometer Maria cable linking Virginia Beach in the US with Bilbao in northern Spain. Maria weighs the same as 24 blue whales, apparently. The firms laying down this serpentine superhighway, worldwide there's now 1.5 million kilometers of undersea data wires, are cagey about how much it costs. But professional estimates indicate a typical transoceanic cable should set you back between 300 and 400 millions of dollars, which seems like a lot because they're not especially thick, typically around the girth of a garden hose. And that includes layers of protective thixotropic jelly around the all-important fiber optic core, plus multiple plastic sheaths and copper wiring to power the thing. But even so, on average, they could ferry an awesome 100 gigabytes per second in data, with newer and forthcoming cables able to transmit 400 gigabytes per second. So how does so much data fit down such slim channels? Part of the answer is an extremely sophisticated data wrangling technique known as dense wavelength division multiplexing. Put simply, dense wavelength division multiplexing lets data providers use more than one wavelength of light to convey information fiber optically. Instead, several wavelengths are employed simultaneously and stacked, creating astonishing data speeds. This happens at buzzing data center-like landing sites at either end of the cable. Are the cables just straightforward long wires? Not quite. Every 70 to 100 kilometers or so along the seabed, cables are punctuated with so-called repeaters. These essentially serve as amplifiers, keeping the signal strength up to par over long distances. That's why the cables incorporate copper conductors, by the way, carrying up to 10,000 volts of DC to power the repeaters. How are the cables laid? They're first coiled into vast cylindrical drums on specialized cable laying ships. As much of the year's planning and charting will go into plotting the perfect transoceanic route. Bad locations for undersea cables include anywhere volcanic or anywhere especially earthquake or mudslide prone, or anywhere heavily trawled by fishermen. The cable is spooled out the back of the ship at a state pace of around 10 kilometers an hour. If the ship encounters bad weather, the captain can decide whether to break off the cord, tie it to a buoy, and retreat to calm waters. When the storm passes, the ship returns to the buoy and picks up where it left off. Accidents and outages on the cables can and do occur. In 2012, Hurricane Sandy in the US knocked out several key transatlantic cables, disrupting networks for hours. In 2011, the Fukushima earthquake in Japan caused similar online cuts. The vast majority of such disruptions, however, are the result of human carelessness, typically trawler nets or wayward ships' anchors. Cables situated close to the shore are significantly more at risk from such disruption. As such, the nearer a land a cable is, the more likely it'll be carefully armor-plated. Many are even dug into the seabed in long dedicated trenches, carved out using ship-drawn plows. Awesomely, sharks have been spotted nibbling on one of Google's subsea cables. Get your teeth into this 2014 claim. More sinister even than that, the US government has consistently warned of interference in the cables from hostile foreign powers like Russia or China. The US government should know all about that. Whistleblower Edward Snowden revealed in 2013 how the NSA had no qualms eavesdropping on fiber optic communications. The geopolitical implications of undersea cables are also fascinating. Last year, the Australian government intervened to prevent Chinese technology giant Huawei from installing a cable connecting Australia with the Solomon Islands. The fear is that China could use the link to gain access to Australia's sensitive internal networks. So who actually owns these cables? That's an interesting question. It's an expensive business, so historically nations or quasi-national telecom providers have picked up the bill. The world's biggest owner of cables remains America's AT&T, with a stake in some 230,000 kilometers of undersea cable. The second biggest owner is China Telecom,
based in
Frequently,
Texas.
cables are owned by groups or consortia of up to 50 separate owners, including tech firms, local government agencies, and other businesses. And while this model helps spread the initial cost, it's less helpful when something goes wrong and nobody can agree who has to put on a wetsuit and do something about it. Increasingly, big tech is recognizing its scope for growth is limited by the undersea cable network. So over the past few years, the overwhelming majority of investment in undersea cable infrastructure has come from companies like Facebook, which currently owns nearly 100,000 kilometers of cables. Google owns roughly the same amount. Amazon has its own massive private network, hooking up the online giant's mighty AWS data centers through cables traversing the Atlantic, Pacific, and Indian Oceans, plus the Mediterranean, and the Red Sea, and the South China Sea. The tech giants like to frame these vast environmentally disruptive infrastructure projects as civilization-enhancing largesse on their minds. But they're also shareholder companies who know perfectly well that increasing the number of human beings online is the only way they can continue to grow. Hang on a second, you're probably thinking, what about Starlink? Isn't our old mate Elon about to make the internet wireless any day now? For now, cable is by far the cheapest and most efficient means of eating vast packets of data over incredibly long distances fast. Even normally bullish Musk says Starlink is only aimed at people who don't presently enjoy access to high-speed fiber. But who knows how that'll pan out in a decade or two. For now, the future is very much undersea cables. Only this summer, Google and Facebook announced a joint initiative to build an undersea cable named Apricot. Apricot will link up Singapore, Japan, Guam, the Philippines, Taiwan, and Indonesia by the year 2024. The longest subaquatic cable ever, a 45,000-kilometer billion-dollar monster called To Africa that will link up 33 nations, was just bankrolled by a Facebook-led consortium. What do you think? Will mankind's ingenious submarine network one day look as obsolete as the telegraph? Let us know in the comments. And don't forget to subscribe for more totally wired tech content.
Okay, come on. So what do you think about that?
Now I know why AT&T charges so much for their internet service.
Yeah, you know, the crazy thing about AT&T is that all that infrastructure that they own, that's all that investment is right here in Texas.
Now,
Uh,
okay, so originally you had PAC, you had Atlantic, you had Southwestern, and then you had just straight up Bell, as far as the telephone companies.
Yeah.
And then eventually all just became AT&T,
Uh,
or is
No,
PAC
I
Bell
think
and
they're
Atlantic Bell
still-
still open,
yeah, they're still
operating as independent?
they're still different. Yeah.
Okay.
There was originally, you know, it was all Bell. And then it was AT&T, and then it got broken up. And deregulation, and then they started growing again.
That's crazy.
But yeah, you know, the whole thing is that when they deregulated, back in the I guess it was early 90s or late 80s, they did not anticipate the global growth that would happen in telecommunication networks.
No. I mean, that's just like everybody talking about back in the mid-90s. Oh, there's never gonna be a gigabit or a gigabyte sized hard drive. That'll never happen. Everybody,
Right.
outside of data centers or servers, no way, never gonna happen. Yeah, okay.
So, you know, the To Africa it's pretty interesting. They said it was the largest undersea cable in the world. And what's pretty amazing about it, I think, is that the people that, even though the people that, I mean, it's led by China Telecom, I think, and there's a couple other European folks that are doing it. But what this means is that between this connecting Africa essentially and Starlink is that the continent of Africa is about to blow up in terms of what is possible And this is pretty amazing for the idea of the global communications infrastructure and what we can do. So this is that picture that
It just means you won't be talking to James in Mumbai at the call center. You're gonna be talking to James in Kenya.
yeah, I mean, that's right. And so but you notice there it's connecting the Great Britain, Portugal, Italy, India. I mean, this is a huge enabler of people around the globe. So it's pretty neat. Pretty neat.
I wonder, it talked about 10,000 volts running through those subsea cables. I wonder at what current though, considering the run that it's got to go,
Oh yeah.
they must have to drive it with an exceeding
Yeah.
amount of current.
And
to go
that's-
that far.
And that's a whole thing about why it's so expensive is because, at every point they have to power enough because they're obviously powering it from both ends, right?
Yep.
So at that, it's basically they have to engineer that midpoint to have enough power.
Yeah, it's not like they have a floating generator in the middle of the ocean to power those repeaters. So
Exactly. But I just wanted you to see that because it's just sometimes it's like we have this perspective when we look at networks to go, okay, that's a switch. Oh, that's a router. Okay, that's a cable. But this stuff is like amazing, right? Even in the fact that I'm like, do you see those ships they had that had the big massive spools and there was like two guys and a huge spool and it's like, oh my gosh. What all goes into making that, from making the cable to getting the ships ready? So if you guys are ever so inspired and you decide you want to go work in that industry, let me know if you get a job there.
Well, heck, you could be like that cat that lived in Maine, won the $1 billion lottery, and then, hey, he could spend half of that on the subsea cables and then make the royalties off of that.
Right. Oh, yeah. That'd be about right. So that's just an example of what is out there in layer one. And it's going to go through real quick. It's got a few minutes, but I want to basically work you up through our OSI model, which is this is a 7-layer model. And you should, I think you've seen this already. There's a million different diagrams of this. And I'm just randomly going through them. So now this is an example of, and you're going to encounter these all over the place, but basically this is a logic model. And a logic model means this is the way we think about something. So physically, all we have is the cable and we have voltage and we have some equipment. But when we have a logic model, it basically gives us the ability to think about something in a very specific way. And so this is the model that we use in networking. That data link layer is that second layer where we link everything together. So I can have all this physical stuff, all the switches, all the devices, and if I don't build a model for those things to interlink together in some way, I don't have anything. And this is a really just as awesome as the physical layer is, and we just saw that, right? With satellites, undersea cables, ships, armor plating, right? The data link layer is just as awesome. There's so much in there. And we're only going to get in this class this tiny, tiny, tiny little piece, which is basically MAC addresses. And a MAC address is the media access control address that every device has. But that's all we're going to get in this class. And I wish I had more time because I could show you some crazy stuff that happens at this layer right here. And one of those things that I will show you is LTE. Who's heard of LTE? Okay. LTE is all layer 2, layer 2, layer 2, layer 2. It doesn't mean LT doesn't stand for layer 2. It stands for long-term evolution. But all of the equipment and everything that happens in LTE is layer 2. So I'm going to look up an EU TRAN, which is the name of the piece of equipment that's there. And because we can get some good diagrams, some good engineering models. So here's the evolved packet core is basically the switch that's inside this equipment, and all the tower sites have the E node Bs, and that's basically the devices that pass those connections. So that's how I can move from point to point, and I don't ever know that that's happening. All that's handled at layer 2. Okay, the technology that is in layer 2 is great, right? So
those E nodes are practically the encoders for the transceivers on the towers.
yeah. So what happened here is this, you see this tower has like what, 3 or 4 panel antennas, right? Okay, so let me scroll and get that. Okay. So each one of these antennas are gonna have, because we got to incorporate technology like MIMO, multi-in, multi-out, right? They're calling it Hydra, right? Where there's 14 or 15 different antennas. All of the pathways that allow that radio signal to propagate in these antennas go on there, and we have to have them geographically aligned properly, so that and there has to be a balance of radio frequencies that allow this to work. All of it has to be geographically controlled. It has to be managed. There's a central location that the FCC actually will control which particular device is on which frequency in which area all across the country. That's all layer 2. Okay, it's a physical layer, but it's still a layer 2 technology. GPS is involved in that. And so I would put out these antennas, and the E node B is the brain that allows all of those antennas to actually pass the traffic back and forth. And then the UEs, those are user equipment, right? That's telephones, laptops, whatever that are there. And then the brain is the EPC. So evolved packet core EPC, and there's a whole network of those EPCs that are at different places, and the EPCs share information about all the users that are on the network, and all that happens before I ever get your data through a gateway onto another type of local network. These are the switches that that's all on my provider network, say Verizon, right, or AT&T. So these are the high-speed switches. that make that technology possible. And that's a high-tech layer 2. Right, so that all happens right here on number 2. All kinds of crazy stuff happens at layer 2. right?
That's me, but I'm not a software engineer.
It's so cool though, because it's like, this is, if you ever seen the movie Inception, right? Where you're like, you go into this rabbit hole, right? And you're having, and what do? They're in people's dreams. And so they're having a dream inside of a dream inside of a dream, and they can get, this is absolutely where we are in this network layer. Because every time we move up, what happens is that we don't really know what happens at the bottom, at the thing below it. So I don't know how, but when I go up to the network layer, when I'm routing things between devices, that's where the routers live on 3. Routers don't know anything that happens on 1 and 2. They don't know how, they don't know whether I use Starlink or undersea cables or something that's in the wall, you know. They have no idea. I get the information to them and then they pass it on to the next router. So if they also don't know what is up here. Okay, they don't know what's inside. They don't know anything about transport.
How much of this, you said that we won't go any deeper than layer 2 in this class. Are you speaking specifically to 13-14 or more in general, all the way through the completion of the program?
I'm gonna get, we're gonna get a little more deeply into switching in Cisco 2 and 3.
Mhm.
We're gonna, what's gonna happen is that the switches are gonna, the switching layer and the routing layer are really gonna merge together.
Okay.
As we get up into 2 and 3, but there's still tons of stuff that we're never going to cover in the beginning layer. So there's a whole nother engineering layer after this that we don't teach. I don't have the
It's outside the scope.
staff, students, or manpower to do that.
Right.
But if you want to go higher in the Cisco hierarchy and do the engineering side, you'll get more of that. Okay, so this is where my IP addresses live at layer 3. Layer 4, we're going to learn about transport. So layer 4 is where we get to decide how we want to send the information. Do we want to send it very carefully, or do we want to send it fast? And so this is where we get to decide between accuracy and speed. And it's an actual choice that we make.
When you say accuracy versus speed, are you talking about like packet loss, or what are you talking about?
Basically, it's about transport. So if I use TCP, transmission control protocol, I have a whole language that's built into how to make sure that what I want to send gets there. And that includes flow control. It includes all these different features that I could build in. It's built into the protocol. If I don't want any of that, and I just want to throw packets at something, and I want to allow my application developer to do his own checking, I can use UDP. So as far as this layer goes right here, I don't know whether there's any control built into it or not if I use UDP. Okay, so there's a little graphic. I'm going to show you this graphic, and this we won't see this again until a couple of weeks. But I put it in here.
No,
Right. So here's the idea. See, throwing that baby. I don't know. The UDP goes, I don't know. I'm just going to pass the data. I don't know anything about how it works.
So is that, I mean, I get the meme.
Yeah.
I understand it,
Mhm.
but with UDP in general, is it more? Would that be utilized in the aspect of, say, just specifically a data server? Where it's read-only access and it's just throwing the data out, it's not receiving and it's not writing anything?
Generally, it's gonna be application specific. So where I would see that, is like VoIP,
Okay.
Netflix, so streaming video, gaming, anything that is prefaced by the word streaming.
Got it.
And so what I do is all I'm doing, and that graphic's a little bit, right, I'm throwing the baby out a little bit on the funny side, okay?
Right.
Because I have this little layer up here called the application layer that is software driven. And so I could easily implement all the things that are built into layer 3. I mean, the TCP model on layer 4, I could easily implement that in software, or I could choose not to. So I'm just giving somebody a choice.
Then at that point, if you're using UDP and you set it up an application, then you end up basically still slowing down or bottlenecking the connection because you're dealing with a software interface that has processor overhead usage.
That's a good question. Would you introduce some issues because of the way I programmed an application? Yeah, I could. And that's not the problem of a network engineer, that's the problem of a software engineer. So that's the difference, right?
Yeah.
I've just given somebody a choice. Okay, so transport layer, I could opt to use the controls built in to the protocol, or I could opt not to. Session layer, this is where it gets a little bit murky, right? These top 3 layers. Maintains connections, responsible for controlling ports and sessions. So the idea here is that if you notice, I have multiple browser tabs open. Okay. I could, these particular applications that are running inside these browser tabs could be sending data up and down the connection, right? Whether I'm looking at it or not. And so that application layer that session layer is basically my network interface card unpacking data and figuring out where it goes. Where do I send this data? Because my web browser is right here. Or my application is right here. How do I basically work through the muck and figure out where everything goes?
So 2 through 7 still are, even though, yes, they're all individually specific on their duties, I use that term loosely, but they're still all technically 2 through 7. It's nothing more than software interface.
Yeah. Yeah, it's all software right here. Now, the note about 6 is there's encryption that occurs there. So ensures that data is in a usable format when encryption occurs. So my 6 is this idea of how does my protocol, HTTP, my transfer protocol that lives up here, establish encryption standards, right? So that's where that encryption lives. So my HTTPS is that I'm sending data through the web, but I have to ensure that there's encryption. So I have to send encryption certificates and do a whole exchange. That happens right here. That's 6. And then 7 is basically the application of making that all happen. And we often joke and say, well, what about layer 8? Where's layer 8? Let me ask this a different way. Who is that layer 8?
Network admins.
The user, me. I'm at layer 8. Now, what that means is, and we're in the age of AI. So this layer 8 may not be a person. It could be a person. It could be an automation process. It could be a robot. It could be an AI. There's lots of things happening at layer 8 that may not be human controlled, but it's user control or from the view of the user. But they don't normally put that in the 7-layer model. Because it wouldn't be a 7-layer model
Is it
anymore.
because it just wasn't previously a thing?
I think it's just an engineer. So this 7-layer OSI model was built a long time before there was necessarily automation. So they didn't really have to think about that in terms of who is doing it. But I often put it in there because I want you to think about it, right? I want you to realize where you are in this model and you're above that. And so I could, when we think about AI, it kind of adds another component. If I'm the programmer that's making the AI, I could be a layer 9 at that point, right? So it's just something to think about. But we're going to go through each one of these models. And in order for us to do something and actually go out and request a web page, in order to open a connection with another server, we have to know where that server is, which means it has to have, we have to get it the IP address. We have to create a communication to go to it. We have to put some data on the wire. And in order to do that, we have to know how actually that process happens. And so we end up back at this data link layer again. And so as that process goes on, we're going to kind of go back and forth between the data link and the physical, or the network layer. In order to get our data over to the point of wherever it ends up going, a destination. So we have this concept of who's the source and who's the destination. So if I am actually making a request, so when I type in Google right here, my browser has to do something. It has to create a request to identify who is Google. And then I become the source of the request, and Google becomes the destination. Now, before I can actually make that happen and get that information from Google, I have to use a DNS service in order to figure out who Google is. And so this is an example of a UDP connection. I'm going to show it to you real quick here. And I'm going to use a little tool called NS Lookup. And this is basically what my browser is doing. It is creating a packet and putting it on the wire to a DNS server, and it's passing that information on to, it's saying, okay, who's google.com, and then the DNS server responds by doing a lookup, and it gives me an IP address.
Hey,
So anytime that I have a host name like google.com in the address bar, I can substitute that with the IP address. And I should get the same information that I would if I typed in google.com. As a matter of fact, it knew what that was and looked it up. So I'm actually doing this. This is an IPv4 address right here. And this is the IPv6 address. It's a longer address. And I get, when I look that up, I get both of them. I'm not running IPv6 here, so my computer doesn't know how to route that. Doesn't know what to do. Okay, that's it for class today. And we'll get into it tomorrow. Anybody have anything real quick for questions?
is there some sort of repository somewhere that holds all of this stuff from the names? Like how do they get it to register on a worldwide set of servers and switches? How does that work?
So that's its own fun thing. I mean, it's totally crazy. There's the answer to that is yes and no. So there's cache servers that are out there in different places. There's root servers that hold the root zones, and then there's individual. Every domain has its own domain zone that they host themselves.
Yeah.
So it's both decentralized and centralized at the same time. It's pretty amazing how it even